Hi everyone, my name is Jonathan Zabalaga and I am a PhD candidate at the Technical University of Munich. Today, I'll be talking about spatial motion planning with Pythagorean Hodograph curves. This is a joint project with Marcus Rui. Our motivation comes from motion planning within constrained and dynamic environments. Given a performance criterion such as navigation time or efficiency, the underlying planning scheme seeks to find the optimal sequence of actions that move the agent from its current state to a goal state without violating system constraints or spatial bounds. Such planners arise across a wide range of scenarios, such as industrial robots in factories, CNC machines with advanced manufacturing capabilities, autonomous mobile robots within warehouses, surgical robots for healthcare, satellites, or space exploration operations. The wide range of scenarios showcases how complex the motion planning problem can be. To tackle this complexity, path-parametric motion planning schemes have shown very attractive features. These schemes assume that the geometric location of interest is given by a function that maps the path parameter to the three-dimensional coordinates of the path. In this presentation, we will refer to this mapping as the path function, and we will denote it by the letter gamma. The fundamental principle underlying these path-parametric planning schemes is to project the three-dimensional Euler coordinates of the system dynamics into a moving frame attached to the parametric path. This moving frame is denoted as the adapted frame, and we will use the notation capital R to refer to it. The spatial states that arise from this projection, the progress along the path, and the orthogonal distance to it, show very appealing attributes for motion planning. This is because it allows to embed the geometrical properties of the environment into the underlying optimization. To conduct this spatial reformulation from the Euler coordinates to the spatial coordinates, state-of-the-art methods rely on the Frenet-Serret frame. Before we discuss the advantages and the limitations of the Frenet-Serret frame, we need to understand how it is defined. If we look into its equations, we realize that the respective components of the frame are exclusively dependent on the path function and its spatial derivatives. At this point, I need to clarify that the spatial derivatives will be denoted by an apostrophe and refer to the derivatives with respect to the path parameter. In the upcoming slides, when referring to time derivatives, we will use the standard dot. Anyway, getting back to the adapted frame of the Frenet-Serret frame, we see that the components are exclusively dependent on the path function and its spatial derivatives. If we look into its angular velocity, we see that it only evolves with respect to the first and the third component, and it does not evolve with respect to the second. Moreover, the change rates associated to this angular velocity are the torsion and the curvature of the path. An additional feature of the Frenet-Serret frame is the fact that both the torsion and the curvature are also exclusively dependent on the path function and its derivatives. Putting these two facts together brings us to the main advantage of the Frenet-Serret frame. Given the fact that the frame and its angular velocity only depend on the path function and its derivatives, the Frenet-Serret frame is extremely analytically simple. This is the main reason why the Frenet-Serret frame is so popular among researchers and among the motion planning community. However, it does come with its own drawbacks. The first disadvantage associates to a singularity that appears in the second component of the frame. This happens whenever the curvature vanishes or the path becomes a straight line. When this happens, the denominator of the second component of the frame becomes 0, and therefore the frame is not defined. This can be very clearly understood by looking into the picture of the slide, where we see that in the transition from a counterclockwise to a clockwise rotation, the Frenet-Serret frame shows a sudden rotation, a sudden flip in the second and the third components of the frame. On top of that, at a very specific location of the transition, the frame itself is not defined. The second disadvantage relates to an undesired twist that appears with respect to the tangent component of the frame. And within the motion planning scenario, this is problematic if we want to ensure a smooth representation of the environment. To understand this, we can compare the rotation minimizing frame to the Frenet-Serret frame at the bottom right part of the slide. We see that the rotation minimizing frame gets rid of this undesired twist and shows a more natural motion of the frame. To tackle these two limitations of the Frenet-Serret frame, we formulated the research question that we are trying to answer in this work. Is it possible to formulate a singularity-free, continuous, and twist-free spatial reformulation of the Euler coordinates by relying on an exact and compact representation of the environment? To understand this question, we have to decouple it into 4 different features. The first one is that we are looking for a singularity-free and continuous spatial reformulation of the Euler coordinates. The reason for this is that we want to make the spatial reformulation compatible with optimization-based algorithms. To do so, we have to ensure that the reformulation is compliant with the underlying solvers, and therefore we have to guarantee the continuity and the lack of singularities. On top of that, we want to deploy this in motion planning scenarios, and therefore we would rather have a smooth representation of the environment, which implies that we need to get rid of that undesired twist. Thirdly, we do not want to compromise the accuracy of the motion planner, and therefore we want to rely on exact and analytical representations of the environment without relying in any sort of approximations. And finally, in order to increase the applicability and to seek real-time applicability, we would like to reduce the amount of coefficients upon which we depend to represent the environment itself. To tackle this question, our contributions are twofold. Firstly, we formulate a novel spatial reformulation that takes no assumptions in the adaptive frame. If you are interested in the specific derivations of this novel spatial reformulation, I suggest that you go over the paper. Anyway, the key message here is the following one. The motion of a 3-dimensional point moving at the speed v, parameterized by psi, with parametric speed sigma, an adaptive frame r, and angular velocity omega is given by the equations of motion shown in the slide. The main distinctive feature of this spatial reformulation is that it does not take any assumptions in the adaptive frame. Therefore, the Frenet-Serret frame-based spatial reformulations applied by state-of-the-art methods are a subset of our spatial reformulation. They are a particular case. Having the freedom to choose the adaptive frame as we desire is a very nice feature because it allows us to get rid of the undesired twist, the discontinuities, and the singularities. At the same time, it brings us a very interesting question, which is the following one. How do we define in closed form the path-parametric functions? So far, we have not formally defined these functions, and the choice of the adaptive frame implies providing a closed form for these expressions. To tackle this question, we need to talk, or we will need to move on to our second contribution. In the second contribution, we identify the appropriateness of Pythagorean Hodograph curves to formulate these path-parametric functions in a closed form. When referring to the Pythagorean Hodograph curves, I will use the term pH curves. pH curves are a broad topic, and due to the time constraints of this presentation, I will just provide a very brief introduction. pH curves are a subset of polynomials whose parametric speed is a polynomial function on the path parameter. Moreover, all the parametric functions relate to 4 polynomials that can be collected under a single quaternion polynomial. This implies that defining the Bernstein coefficients of the quaternion polynomial is sufficient to provide the closed form for all parametric functions. In other words, for a pH curve of degree 2n+1, it is sufficient to define 4n+1 Bernstein coefficients in order to obtain or to fully define the parametric functions. Putting together these two main ingredients or two main contributions, on the one hand, the spatial reformulation that does not take any sort of assumptions in the adaptive frame, and on the other hand, the Pythagorean Hodograph curves, which allow us to calculate the path-parametric functions, leveraging, like putting these two together and leveraging their combination, we exploit them in the motion planning problem. And what the main feature that we exploit out of them is the fact that we enhance spatial awareness. Before we discuss how we convert these concepts into a motion planning approach, it is important to clarify what assumptions we make in the environment representation. Given a starting location and a goal location, we assume that the obstacle-free space is given by a combination or by multiple, it's decomposed into multiple convex sets. This decomposition can be assumed to be a solved problem because there is prior work that already does this. So, assuming that the obstacle-free space is decomposed into multiple convex sets, we propose a dual-stage motion planning approach. In the first stage, we solve an optimization problem in order to compute a collision and twist-free pH spline. The coefficients found from this spline, or the coefficients associated to this spline, are fed into a secondary prediction-based stage. This stage, more specifically, it's an NMPC controller whose plan model contains the spatially reformulated system dynamics. Using this spatially reformulated plan model allows to exploit the available space to achieve the desired performance. Finally, the optimal control commands obtained from the second stage are fed into the system that we want to control. To evaluate our approach, we conducted a case study consisting of a non-convex three-dimensional space. The respective starting point and ending point can be visualized in the animation at the left-hand side, while the associated convex decomposition is attached in the animation at the right-hand side. As an illustrative example, we chose a system that was a point mass with acceleration constraints. And the desired performance or desired behavior was chosen to be the progress maximization. To understand the computed results or the obtained results, we will decouple them according to both stages. First of all, we compute the collision-free and twist-free pH spline. The resultant pH spline, or the adapted frame resulting from this computation, can be seen at the left-hand side by the isometric view, the top view, and the side view. As we've already said, every pH spline, or all the parametric functions associated to the pH spline, relate to a quaternion polynomial. And the components of the quaternion polynomial are attached at the top right side of the slide. These graphs show that in order to have parametric functions which are C2, we need a quaternion polynomial that is C3. After computing the pH spline and after obtaining the coefficients of this pH spline, we embed them into the second stage, where we run the NMPC. The trajectory resulting from the NMPC is attached or is shown by the colored line in the left side of the slide. The respective states, the respective spatial states, are shown in the right bottom part of the slide. This trajectory characterizes for the fact that not only it exploits the actuation of the system, but it also leverages the available free space. This can be understood by looking into the trajectory and realizing that the trajectory touches the apexes of the curve. And at the same time, if we look into the accelerations, we realize that throughout the entire navigation, one of the components of the acceleration always remains saturated. Putting it in a nutshell, the presented method shows three appealing properties. First, the compact parameterization of the free space into a handful of coefficients accounts for its efficiency. Second, having the environment's geometric properties embedded into the optimization eases the formulation of collision-free navigation algorithms. Third, the method's versatility is exposed by its compatibility with any prediction-based motion planner, making it applicable to any cost function and deployable in any system. As a closing remark, let's analyze how our work addresses the proposed research question. Given that our method makes no assumptions about the adaptive frame, the spatial reformulation presented in the first contribution not only is singularity-free and continuous, but also shows capable of being twist-free. Moreover, by utilizing pH curves, we are able to exactly compute the parametric functions, eliminating the need for approximations. Finally, because these curves are based on a small number of coefficients, a compact representation of the environment is also achieved. This is everything from my side. Thank you very much for your attention.